Welcome. Today we are going to solve three problems under the topic Routh Hurwitz Criteria. So coming to the 31st question, a plant transfer function is given as g of s, and when the plant operates in a unity feedback configuration, the condition for the stability of the closed loop system. So we have to find the condition for the stability of the closed loop system. So here the h of s is unity. So the h of s is unity, and g of s is given as kps plus ki by s square by s plus 2, and we know that transfer function, closed loop transfer function, is g of s by 1 plus g of s h of s. Just substitute the g of s and h of s, which is unity, and find out the characteristic equation, which is given by 1 plus g of s h of s equal to 0. So you will get this equation. Yes, and then apply your Routh's array. That is, first row is alternative coefficients of the characteristic equations, and then the third row is given by the cross determinants minus negative of the determinant, that is 2 kp minus ki divided by the first column element. So just construct the Routh array, and from Routh's array you have to decide because the first column elements should be positive, right? So this term should be positive and also this term should be positive. So it infers that 2 kp minus ki by 2 is greater than 0, and also ki is greater than 0. So, and from this, simplify this equation, you will get kp is greater than ki by 2, and which is greater than 0. So hence the answer is A1. So coming to the 33rd problem, here a unity feedback system that uses proportional integral control is shown in the figure. So here the stability of a overall system is controlled by tuning the PI control parameters kp and ki. The maximum value of ki that can be chosen so as to keep the overall system stable, or in the worst case marginally stable. So you have to find out just construct the Routh's array from the characteristic equation of this feedback control systems, and after constructing the Routh's array, just find the value for the condition for ki and kp, and from that we have to find the maximum value of ki for the system to be stable, or at least marginally stable. So for this, first we will find the g of s. So g of s is given, so just get the g of s from the diagram, and it is shown that h of s is 1 because it is unity feedback, and substituting in the closed loop transfer function you get the equation, and just find the characteristic equation, and from the characteristic equation, first we know that all the coefficients of characteristic equation must be greater than 0 or positive for the necessary conditions. Yes. So from the characteristic equation we infer that 2 plus 2 kp should be greater than 0, as well as 2 ki should be greater than 0. That is what I have written here. So both must be greater than 0. On simplifying this, you will get kp is greater than minus 1 and ki is greater than 0. And after that you just construct the Routh's array from the characteristic equation, and you have to determine the stability, right? So for the system to be stable, all the elements in the first column should be greater than 0. So this should be greater than 0, and also this term should be greater than 0. So first we take 18 minus 2 kp by 4 should be greater than 0. So from this we can infer that kp is less than 9, and also from the necessary condition we infer that kp is greater than minus 1. So on combining these two, we can write as minus 1, kp is greater than minus 1 and less than 9. Okay, and coming to the second one, this second element, that is the element in the first column should be greater than 0, right? So by equating, you will get Ki should be less than minus 4 kp square plus 32 kp plus 36 divided by 32. And we know that Ki should be greater than 0, that we inferred from the starting necessary condition, that is 2 Ki is greater than 0, so Ki is greater than 0. So you know, so from those two you can combine and write it as Ki is greater than 0 and less than this term. Okay, and we have to find the maximum value of Ki. So for this, just take this equation, because Ki is less than this equation, right? So just take this algebraic equation and differentiate it with respect to Kp, so that you will get the maximum value for Kp. So just take this characteristic or auxiliary equation and just differentiate with respect to Kp, so that you will get the value for Kp. So this is the value of Kp at which Ki will be maximum, and then substitute the Kp value, Kp is equal to 4, in this characteristic equation. You will get the auxiliary equation. You can say this as an auxiliary equation, and just substitute the value of Kp here, so that you can find the maximum value of Ki. So that is 3.125. Yes. Coming to the next question, 34th question. Here the characteristic equation of the closed loop system is 10s power 4 minus s cube plus 5s square plus s plus 1 equal to 0. So we have to find whether the system is stable or unstable or marginally stable. So it's very on seeing this equation, you can easily determine the stability of the system, because if you see, there exists a negative here. Yeah, the coefficient is negative in this characteristic equation, which infers that the necessary condition is not satisfied. So hence we can say that the system is unstable. So the answer is A choice, unstable. Yes, that's all.